Hello, and welcome to Slice of Physics. I'm going to be telling you some more about forces created by magnetic fields. So I'll talk about two things. First, I'll talk about forces on current-carrying wires that are created by magnetic fields. And then I'm going to talk about forces on particles that magnetic fields create that act on particles and what effect those have. So first of all, the wires. So we know that magnetic fields create forces on particles. So for instance, if I have a positive charge and it is moving upward, and let's say that there is a magnetic field around it pointing into the page, then you can use the right-hand rule to find out which direction the force will go. So if this is the velocity of the particle, then you can find out that the force will be in that direction. So it's not too hard to imagine that if I have a wire with many charges flowing upward, and that's sitting in a magnetic field, then we might expect that because the current is just made up of particles moving upward, that there would be a similar force pointing to the left if this is the direction of the current. Okay, so how strong is that? How strong is that force? We know that the force of the magnetic field on a moving charged particle is QVB, and there's also a sine alpha for the angle between the velocity and the magnetic field. So the force of the magnetic field on a wire, well, what could it be that could come into this picture? Well, the magnetic field is probably important. And we also want to say that if there's a large current, there should be more force on a large current than on a small current. So there's probably an I in there, the current. And we also would expect that the force on a long wire would be more than the force on a short wire. So there's also an L here. So the force on the wire is the current times the length of the wire times the magnetic field. So if I have a wire like this, and if there's a magnetic field that points up, then there would be some sort of force on it, ILB. On the other hand, if the magnetic field points diagonally, we might expect that there would be a less force, because we know that if the magnetic field points horizontally, then then there's no force, because we remember that when particles move in the direction of the magnetic field, then there's no magnetic force on them. So we might expect that the angle, again, would have something to do with this force. So there's the formula for the force of a magnetic field acting on a wire. Okay, so I want to talk about one more thing, which is the force of a magnetic field on a particle and what that does to the particle, what motion that creates in the particle. So let's suppose that there's a magnetic field which is pointing into the page, and let's suppose I start a positive charge at this point, and let's suppose that it starts going down. So you can use the right-hand rule to find out that if this is the direction of the velocity of the particle, that the force on the particle points in this direction. So what do we expect is going to happen at this point? Well, the particle is moving downward, The force doesn't change its motion right away. Forces don't change motion instantaneously, they gradually change the motion. So it starts to curve around to the right. Okay, now what happens? So it's gone on this curved path. Well, now its velocity points in a different direction. It points here. So that means that you can use the right-hand rule again to find out that the force points in that direction. So that means that the force is going to gradually pull the particle in that direction. And it goes on a curved path, and eventually it curves here. And then at this point, you can use the right-hand rule to say that if the velocity of the particle is in this direction, then the force points in that direction. So you can see that what's going to happen is that the particle is going to go around in a circle. And it's going to eventually come right back to where it started. So that would be true of a positive particle. If I put a negative particle in a magnetic field and I started it going down in this way, and the magnetic field was pointing into the page, then it would go on the opposite trajectory. And it would go around in a circle and come back to where it started. So how do we find the shape of the circle? Well, what we really need to know is the radius of the circle. So we know that the centripetal force, remember the net force for circular motion is called the centripetal force, and the centripetal force is equal to mv squared over r, where r is the radius of the circle, v is the speed of the particle. And we also know that that force is qvb. It's the magnetic force. So this must equal qvb. So let's say we know the mass of the particle, its speed, and its charge, and the magnetic field. Can we find the radius of the circle that it goes around? Well, we have this equation here. So let's divide both sides by v. So we have mv over r equals qb. And then let's multiply both sides by r. So we have mv equals qbr. And then let's divide both sides by qb. So we have mv over qb equals r. So that is the formula for the radius of the circle that a particle goes around. So if you release a particle in a magnetic field, a charged particle in a magnetic field, it will go in a circle, or it may go in a helical path. So for instance, if there's a magnetic field like this, and I take a particle and I start it going in this direction, then it may go around the field lines in a spiral shape. So these are the two possibilities for the motion of a particle in a magnetic field, charged particle. It may go in a circle, or if it has some motion in the direction of the field, it would spiral around the field lines in this shape. Okay. So we've learned about the force that a magnetic field exerts on a current carrying wire, which is F equals ILB sine alpha. And we've also learned about the circles that a charged particle will go around when it's released in a magnetic field, which has radius r equals mv over qb. Okay.